welcome to this deep dive. We've got quite a stack of source material here, ready to unpack.
Yeah, all about some really fundamental chemistry.
Absolutely. Our mission today is to sort of cut through the complexity, pull out the core insights from solution chemistry. We're talking acids, bases, and those super important oxidation reduction reactions, redox.
Exactly. If you've ever wondered, how stomach acid works or how a battery actually generates power.
Or even just why stuff rusts.
Right. You're already touching on these concepts. So we're aiming to connect those dots from the, let's say, definitions all the way to the real world stuff. Hopefully give you some aha moments without drowning you in jargon.
Think of it as maybe a shortcut to seeing the chemistry that's happening all around you, but, through a clearer lens.
Sounds good.
So let's start right at the beginning. What actually makes something an acid or a base? Because, well, even that basic idea has changed over time.
It really has. The first definition most people run into is probably the Arrhenius one. Simple idea, but it's limited because it only talks about water. An Arrhenius acid is something that releases Hay ions in water.
Like hydrochloric acid, HCl, gives you hay in clay.
Exactly. And an Arrhenius base. That releases hydroxide ions, NO, out in water.
Sodium hydroxide, NaOH. Gives NaOH and OHO. Easy enough, but like you said, limited.
Yeah, because what about ammonia, NaO? It acts like a base in water, makes the water basic, but it doesn't have an OO group to release. Arrhenius can't really explain that easily.
Okay.
Yeah.
Which is why we need something broader.
Exactly. That's where the Brunstad-Lowry definition comes in. It's much more useful generally. It shifts focus from, what ions pop off in water to the actual transfer of a proton, an AON.
So under Brunstad-Lowry, an acid is simply a proton donor.
Proton donor, yep. And a base.
A proton acceptor.
A proton acceptor. And what's cool about this definition is it immediately brings in this idea of conjugate pairs.
Right. When an acid gives away its proton.
The thing left behind, that's its conjugate base.
And when a base accepts a proton.
It becomes its conjugate acid. They come in pairs.
Like HCl donates its proton, leaves Cl, that's the conjugate base.
Perfect. And ammonia, NHR, accepts a proton.
Becomes NHR ammonium, its conjugate acid.
Exactly. That pairing is really fundamental to thinking about acid-base reactions this way.
And water itself is kind of the star player here, isn't it? It can swing both ways.
It's amphoteric, yeah. It can donate a proton, acting as an acid, or accept one, acting as a base. Depends what else is in the beaker.
And when we talk about that H ion in water,
Right.
It doesn't just float around alone, does it?
No, not really. That proton, H, is so reactive, it immediately grabs onto a water molecule. So what you actually have is the hydronium ion, HR.
So H in water really means HR most of the time.
Good point. Now there's one more level, even more general, the Lewis definition.
Okay.
This one steps away from protons entirely. It's all about electron pairs.
Right. A Lewis acid accepts an electron pair.
And a Lewis base donates an electron pair.
This is super important for reactions that don't even involve hydrogen, right? Like metal ions reacting or lots of organic chemistry.
Absolutely. It's the broadest framework. But for day-to-day aqueous stuff, Brunstad-Lowry is often, the most practical way to think about it.
Okay, so we've got these layers of definitions. Arrhenius, Brunstad-Lowry, Lewis.
Yeah.
But you mentioned water. Let's dig into water itself a bit more. Because even pure water isn't completely inert.
Not at all. It actually undergoes this thing called self-dissociation or autoionization, just a tiny bit.
Water molecules bumping into each other.
Yeah. One water molecule can donate a proton to another. So you end up with a small amount of HASO and OHO ions, even in absolutely pure water.
And there's a constant for that equilibrium, right? Kw.
That's the one. The ion product of water, Kw. At standard temperature, 25 degrees C, the concentration pH times the concentration of OO is always this tiny constant value. 1.0 times 10 to the minus 14.
Material. Wow. That's
very small. And it's a constant product. So if something makes the HU concentration go up, the OA has to go down to keep that product the same, and vice versa.
in dealing with numbers like 10 or 10 oro, it's kind of awkward, which I guess is why we have the pH scale.
Exactly why. It's a logarithmic scale. Makes life easier. pH is defined as the negative base 10 logarithm of the hydrogen ion concentration. So pH equals dash log A.
It just turns those tiny scientific notation numbers into, more manageable numbers, usually between 0 and 14.
Precisely. And you can do the same for the hydroxide concentration. That gives you POH. So POH equals dash log AO.
And because of that KOA relationship, HO times OA equals 10-OR.
If you take the negative log of that whole equation, you get a really neat result. pH plus POH equals 1400 at 25 degrees C anyway.
That's super useful. They're linked. If you know one, you know the other.
Yep. And this gives us the pH scale we all kind of know.
Below 7 is acidic.
Meaning more Ho than OA.
Exactly. 7 is neutral.
Equal amounts of H and OA, like pure water.
And above 7 is basic, or alkaline.
Where you've got more OO than ERA. It's just a quick way to tell what's going on with those ion concentrations.
Okay, so that's pH. But, like, vinegar is acidic and battery acid is acidic. They're not the same strength, are they?
Not at all. And that's the crucial difference between strong and weak acids and bases. Really important distinction.
So a strong acid, like HCl, hydrochloric acid.
It essentially dissociates completely in water. Every HCl molecule gives up its proton. Bang. Done. Same idea for a strong base like NaOH, sodium hydroxide. It completely breaks apart into NaO and OO ions.
But weak ones are different.
Totally different. A weak acid, like acetic acid, the stuff in vinegar, only partially gives up its protons in water.
It sets up an equilibrium.
Exactly. Most of it stays as undissociated acetic acid molecules. Only a fraction forms ASA and acetate ions. Same logic for a weak base, like ammonia. It only partially reacts with water to accept protons and makes them OO. That partial reaction is why they're called weak.
Okay, and we need a way to measure how weak they are. That's K and Kb.
You got it. K is the acid dissociation constant. It's just the equilibrium constant for that reaction where the weak acid gives a proton to water.
HAH plus AO, so KO plus A.
Precisely. A larger chi value means the equilibrium lies further to the right. More products, more dissociation. So a larger chi means a stronger weak acid.
But we often see pico instead, like pH.
Yep, same logic. Pico is this log-oro. Because K values can be small and awkward, pK puts them on a nicer scale. But remember, it's a negative log. So a smaller pico actually means a larger chi, which means a stronger weak acid.
Smaller pico, stronger acid.
Yep.
Got it. And Kb is the same idea for bases.
Exactly the same principle. Kb is the base dissociation constant. Measures how much a weak base reacts with water to make hydroxide ions. OS, larger Kb, stronger weak base.
And pKb equals smaller pKb.
Stronger weak base.
Okay. Now you mentioned conjugate pairs earlier. How do K and Kb relate for a conjugate pair? Like acetic acid and the acetate ion.
There's a really fundamental link there. For any weak acid and its conjugate base, their strengths are inversely related.
Meaning if the acid is stronger.
Its conjugate base must be weaker, and mathematically it works out beautifully. Ka for the acid multiplied by Kb for its conjugate base equals Kw.
KXKB. Kb equals Kw. Wow.
Yep. And if you take negative logs again...
pKa plus pKb equals pKb, which is 14 at 25 degrees C.
Exactly. pKa plus pKb equals 14. That tells you immediately if you have a weak acid with a small pKa, meaning it's relatively strong for a weak acid.
Then its conjugate base must have a large pKb, meaning it's a very weak base.
It's a seesaw. You can't have both be strong, you can't have both be weak. This relationship is absolutely essential for understanding probably the coolest application of weak acids and bases. Buffer solutions.
Buffers, right. These are the solutions that, like, resist changes in pH.
That's their magic trick. You can add a bit of acid or a bit of base, and the pH barely budges. They act like chemical shock absorbers for pH.
How do they do that?
Well, the key is what they're made of. A buffer contains a significant amount of both a weak acid and its conjugate base. Or you could have a weak base and its conjugate acid. That pair is crucial.
So if you add some extra acid, some H ions.
The conjugate base component that's already in the buffer solution steps up and reacts with those added Ho ions. It essentially gobbles them up, turning them back into the weak acid.
So the added Haley doesn't really increase the overall high concentration much.
Exactly. And if you add a base, some O ions.
Then the weak acid component of the buffer donates its proton to the OHAO, neutralizing it, turning it into water and the conjugate base.
Right, again. So the added base gets neutralized too. The buffer components sacrifice themselves, if you like, to soak up the added acid or base, keeping the overall pH relatively stable. That's the principle of buffer action.
There's an equation for this too, isn't there? Henderson-Hasselbalch.
Ah, yes, the Henderson-Hasselbalch equation. It looks like pH is approximately equal to pK plus the log of the ratio of the conjugate base concentration to the weak acid concentration.
THR plus log, base acid.
Yeah. What it tells you is that the pH of the buffer is really set by two things. The pK of the weak acid you chose.
And the ratio of how much base form versus acid form you put in.
Right. And notice if you have equal amounts of the weak acid and its conjugate base, that ratio is 1. and the log of 1 is 0.
So pH equals pKk.
Exactly. That's typically the point where the buffer works best. It has maximum capacity to resist changes in either direction. The useful range for a buffer is generally around the pK plus or minus 1 pH unit.
And where do we see these in action? I mean, besides the lab?
Oh, everywhere. The most critical example is probably your own blood.
Right. It has to stay at a very specific pH, around 7.4.
Incredibly tightly controlled. If it deviates much, you're in serious trouble because your enzymes, all your proteins, stop working correctly. And that stability is maintained by several buffer systems working together. The bicarbonate buffer system, carbonic acid and bicarbonate ion, is a major one.
So this isn't just like theoretical chemistry, it's life and death stuff.
Literally. Makes you appreciate pKa values.
Definitely. Okay, so we've covered adding acids and bases. But what about salts? You dissolve something like table salt, NaCl, in water. That should be neutral, right?
That one is, yes. But not all salts dissolve to give neutral solutions. This is where salt hydrolysis comes in.
Hydrolysis, meaning reaction with water.
Exactly. Remember, a salt is made from the cation of a base and the anion of an acid. When you dissolve the salt, those ions are released. The question is, can either of those ions react with water and change the pH?
Okay, how do we know?
You have to think about where the ions came from, their parent acid and base.
So NaCl, NaCl comes from AOH, a strong base. ClO comes from HCl, a strong acid.
Right, and the conjugates of strong acids and bases are incredibly weak. So weak, they basically don't react with water at all. NaCl doesn't act as an acid, Cl doesn't act as a base. Result, neutral solution, pH 7.
Okay, that makes sense. But what if the salt involves a weak acid or base, like a sodium acetate, just CuNa?
Good example. NaRO is still from NaOH, strong base, so it's neutral. But acetate, CaCOO, that's the conjugate base of acetic acid, which is a weak acid.
Ah. So if acetic acid is weak, its conjugate base, acetate, must be relatively strong. Strong enough to act as a base.
Strong enough to act as a weak base, yes. It can accept a proton from water molecules. CaCOO plus H-arrow gives you CaCOO plus OHO. It produces hydroxide ions.
Making the solution basic.
Exactly. Dissolving sodium acetate makes the water basic because the acetate ion hydrolyzes.
Okay, flip side. What about ammonium chloride, NaClO?
Okay. Clay is from HCl, strong acid, so it's neutral. But NHAir, ammonium, that's the conjugate acid of ammonia, NHAir, which is a weak base.
So if ammonia is a weak base, its conjugate acid ammonium must be strong enough to act as a weak acid.
You got it. NHAir can donate a proton to water. NHO plus HO gives NHO plus HO. It produces hydronium ions.
Making solution acidic?
Precisely. So dissolving a salt from a strong acid and a weak base gives an acidic solution. It all comes down to whether the cation is a weak acid or the anion is a weak base. Their parentage tells the story.
That clarifies a lot. Now, speaking of basic solutions, we often hear the word alkaline. Is that just another word for basic?
Often, yes. In everyday chat or even some industries, alkaline just means pH greater than 7. Basic.
But it has more specific chemical meaning too.
It can, yeah. Chemically, it often refers more specifically to substances that are soluble in water and show strong basicity, particularly the hydroxides and carbonates of the alkali metals group 1, like sodium, potassium, and some of the alkaline earth metals group 2, like calcium, barium.
So things like NaOH, Li, or KOH.
Exactly. Those are classic alkalis. The name itself actually comes from Arabic alkali, which meant plant ashes, because if you dissolved wood ash in water, you got a basic solution.
Why?
Because wood ash contains potassium carbonate, KSO. Carbonate is the conjugate base of the weak acid bicarbonate, so it hydrolyzes water to make OO, an alkaline solution.
Ah. So industrially, alkalis are often those strong soluble bases like sodium hydroxide used in soap making, paper, cleaning.
Right. While basicity is the general property, pH 7, alkalinity often implies these stronger soluble bases or solutions made from them. Just a bit of nuance depending on context.
Okay, context matters. Got it. Right, let's shift gears now. We've done proton transfer with acids and bases. What about the other major transfer in chemistry?
Electron transfer.
Electron transfer. The world of oxidation reduction reactions. Or just redox.
Redox, yeah. And these are absolutely everywhere. I mean, they power life itself. Cellular respiration is redox. Batteries, corrosion, combustion, it's all redox.
Fundamentally, it's just reactions where electrons move between substances.
That's the core idea. One substance loses electrons, another one gains them.
Okay, let's break down the terms. Oxidation is...
Oxidation is loss. OLL, loss of electrons.
OIL. Okay. So if something is oxidized, it loses electrons.
Right.
like sodium metal becoming a sodium ion, RuNO plus E.
Perfect example. And reduction.
Reduction is gain. Rig, gain of electrons.
Rig. Like chlorine gas gaining electrons to become chloride ions. Cellulo plus 2E to CeLO.
And the crucial point is they always happen together, right?
Always, always, always. You can't have oxidation without reduction and vice versa. Electrons have to come from somewhere and go somewhere. It's a transfer.
Okay, so how do we keep track of where the electrons are moving, especially in more complicated molecules?
That's where we use oxidation numbers, sometimes called oxidation states. It's basically a bookkeeping system. We assign a sort of hypothetical charge to each atom in a compound, as if the bonding electrons were completely transferred.
There are rules for assigning these numbers, right? Like oxygen is usually Nenica 2, hydrogen plus 1.
Yeah, there's a set of rules. Element by itself is 0. Simple ion is its charge. Oxygen usually Nenica 2, except peroxides. Hydrogen usually plus 1, except metal hydrides. Sum in a neutral compound is 0. Sum in an ion equals the ion's charge. By following those rules, you can assign an oxidation number to every atom.
And then you look for changes during the reaction.
Exactly. If an atom's oxidation number increases,
That means it became more positive or less negative. So it must have lost electrons. That's oxidation.
correct. And if an atom's oxidation number decreases,
It became less positive or more negative. It must have gained electrons. That's reduction.
let's use that copper oxide example again. CuO plus HuO plus H0.
Okay, in CuO, oxygen is NaNO, so copper must be plus 2 to balance it.
Right. On the product side, elemental copper Q is just 0.
So copper went from plus 2 to 0. Its number decreased. It was reduced.
Perfect. Now hydrogen. In H0, it's an element, so it's 0.
In H0, oxygen is -2. Each hydrogen is plus 1.
So hydrogen went from 0 to plus 1. Its number increased. It was oxidized.
Copper reduced, hydrogen oxidized, happened together.
Always. Now, this leads to the idea of oxidizing and reducing agents.
Okay, the agent is the thing that causes the change.
Exactly. The substance that causes something else to be oxidized is called the oxidizing agent, or oxidant.
How does it cause oxidation? By taking electrons away.
Precisely. It accepts electrons from the substance being oxidized, which means the oxidizing agent itself gets reduced.
Ah, the oxidizing agent gets reduced.
And the substance that causes something else to be reduced is the reducing agent, or reductant.
It causes reduction by giving electrons.
Yep. It donates electrons to the substance being reduced, which means the reducing agent itself gets oxidized.
So the reducing agent gets oxidized. It's kind of backward from the name, isn't
It
it?
trips people up all the time. Just remember, the agent does the action to something else and undergoes the opposite process itself. Oxygen gas, OJO, is a classic oxidizing agent. It gets reduced. Metals, hydrogen gas, carbon, they're often reducing agents. They get oxidized.
Okay, oil, air, A agent gets the opposite. Got it.
Right.
Now, can we quantify like how much something wants to be reduced, like a reduction strength?
We can. That's what electrode potential is all about.
Electrode potential, symbol E. It measures the tendency of a substance to gain electrons, to be reduced.
That's the idea. And when we measure it under specific standard conditions, 25 degrees C, 1 atmosphere pressure for gases, 1 molar concentration for solutions, we call it the standard electrode potential, E degrees, often specifically called the standard reduction potential.
And these are always measured relative to some 0 point.
Yeah, you need a reference.
Okay.
The universally agreed reference is the standard hydrogen electrode, or SHE. It involves bubbling hydrogen gas over a platinum electrode in a 1M acid solution. Its standard potential is defined as exactly 0.000 volts.
So all other E degree values are measured compared to that SHE being 0.
Correct. So what do those E degree values tell us?
Well, if a substance has a large positive E degree value,
It means it has a strong tendency to gain electrons compared to hydrogen ions. It's easily reduced.
which makes it a strong oxidizing agent.
Exactly. Fluorine gas, FUR, has a very large positive E degrees. It desperately wants electrons, strongest oxidizing agent there is.
Okay, and if a substance has a large negative E degree value,
That means it has a very low tendency to be reduced compared to hydrogen. It's hard to force electrons onto it. It would much rather lose electrons.
meaning it's easily oxidized, so its reduced form must be.
A strong reducing agent. Lithium metal, Li, comes from reducing Li, which has a very negative E degrees. So lithium metal is a powerful reducing agent. It readily gives up its electron,
So these E degree values basically rank everything's ability to pull electrons.
pretty much. And you can use them to predict whether a redox reaction will happen spontaneously. If you combine the reduction half-reaction E degrees and the oxidation half-reaction E degrees, remembering to flip the sign for oxidation, if the overall cell potential E degrees, E degree reduction, E degree oxidation is positive.
The reaction should go. Electrons will flow spontaneously.
Right. And if it's negative, you'd need to put energy in, like an electrolysis to make it happen.
There's also something called the Nernst equation. Does that fit in here?
Yeah, the Nernst equation is important because standard conditions, 1m, 1 at dm, are rare in the real world. It adjusts the electrode potential based on the actual concentrations and pressures. It tells you how the driving force changes when you're not at standard state. But the basic idea is E degree tells you the inherent tendency.
Okay, fantastic. So we've built up this toolkit: acid base, pH, pKa, redox, oxidation numbers, E degrees. Now let's put it all together and look at some real-world applications where this stuff is really happening.
Perfect. And a classic everyday example of redox gone wild is metal corrosion, rusting.
Right. You said it's electrochemical, like those tiny batteries.
Exactly like that. On the surface of, say, iron, you get tiny anodic and cathodic regions setting up, often due to impurities or stresses in the metal or just variations in oxygen access, a local electrochemical cell.
So at the anode spot.
The iron metal itself gets oxidized. Fe atoms lose electrons, becoming Fe ions that dissolve maybe in a thin film of moisture. Fe plus 2e, that's the oxidation.
And those electrons have to go somewhere. The cathode.
Yep. They travel through the metal to a nearby cathodic spot. There, they're usually picked up by oxygen from the air, which reacts with water. O plus 2H plus 4EO plus 4EO, that's the reduction.
So you've got FeO ions and O ions forming near each other.
And they react. Plus, the FeO often gets further oxidized by oxygen to FeO. The end result is this horrible, flaky mix of hydrated iron oxides and hydroxides. That's rust.
And things like salt water make it worse.
Oh, yeah. The dissolved salt ions make the water more conductive, allowing the ions in the electrochemical cell to move around more easily. Accelerates the whole process dramatically. That's why cars rust faster where roads are salted.
Makes sense. So preventing corrosion is all about stopping that electrochemical cell.
Pretty much. Or at least slowing it down or redirecting it.
Like painting it, just putting a barrier between the metal and the environment.
That's the simplest way. Coatings, paint, plastic enamel, just block the oxygen and water. Or you can plate it with another metal.
Like tin cans. Steel plated with tin.
Right. Tin is less reactive than iron, so it provides a good barrier if it's intact. But if you scratch a tin can, now you've exposed the iron, and it's in contact with the less reactive tin. The iron becomes the anode, the tin becomes the cathode, and the iron actually corrodes faster than it would have alone at the scratch site.
Yikes. Not ideal. What about galvanizing? Coating steel with zinc.
Now that's clever. Zinc is more reactive than iron. It has a more negative electrode potential.
So if you scratch galvanized steel.
The zinc preferentially corrodes. It acts as a sacrificial anode, getting oxidized, ZnU-all4 plus 2e, instead of the iron. The zinc sacrifices itself to protect the steel.
That's why they bolt big blocks of zinc or magnesium onto ship hulls and pipelines.
Exactly that principle. Sacrificial anodes. Cheaper to replace the zinc block than the whole steel structure.
What else? Cathodic protection.
That's another electrical method. You use an external power source to pump electrons into the metal structure you want to protect, forcing it to be the cathode so it can't oxidize. Used for pipelines, bridges.
And passivation. I hear that for stainless steel.
Right. Some metals, like aluminum, chromium, which is in stainless steel, titanium, they react with oxygen very quickly, but they form an incredibly thin, tough, non-porous oxide layer right on the surface.
And that layer seals the metal underneath.
Exactly. It passivates the surface, preventing further corrosion. Stainless steel's stainlessness comes from that chromium oxide layer constantly reforming if scratched. Alloying is another strategy, mixing metals to improve properties, including corrosion resistance.
It's amazing how many ways there are to fight rust, all based on manipulating that redox chemistry.
It's a constant battle.
Okay, let's shift from metals to something biological. Proteins.
Yeah.
How do acid base and redox affect them?
Oh, profoundly. Proteins are these incredibly complex folded chains of amino acids, and their specific 3D shape is absolutely vital for their job, whether it's being an enzyme or a structural component.
And acids and bases can mess with that shape.
Big time. First, really strong acids or bases, especially with heat, can actually break the peptide bonds holding the amino acid chain together. That's hydrolysis, breaking the primary structure.
But even just changing the pH without breaking the chain.
That causes denaturation. See, amino acids have side chains, and many of these contain acidic groups like NaCOH or basic groups like NHNH.
Yeah, their charge depends on the pH.
Exactly. NaCOH group might be neutral at low pH, but negatively charged at higher pH.
Huh?
And NH2O's group might be positively charged at low pH and neutral at higher pH.
So changing the solution's pH changes the charges all over the protein molecule.
Right. And those charges are crucial for the interactions, the ionic bonds, the hydrogen bonds that hold the protein in its specific folded shape.
Yeah.
If you change the charges, those bonds break or form incorrectly, and the protein unfolds or refolds wrongly. It denatures.
And loses its function. Like cooking an egg white, the heat and pH changes denature the albumin protein.
Perfect example. There's also a specific pH for each protein, the isoelectric point, PI, where its net overall charge is 0. Proteins are often least soluble and might aggregate or precipitate out at their PI.
So pH control is critical for proteins. What about redox?
Redox comes into play mainly through one specific amino acid, cysteine. Cysteine has a thiol group, FH, on its side chain.
Okay.
Two cysteine residues, maybe far apart in the chain but brought close by folding, can react under oxidizing conditions. Their SNH groups lose hydrogen and the sulfurs bond together, forming a disulfide bond, SS.
Like a little bridge locking the protein structure.
Exactly. These disulfide bonds are really important covalent crosslinks that help stabilize the 3D shape of many proteins, especially ones that exist outside of cells.
And you can break them with reduction.
Yep. Reducing agents break the SSS bond back into two SSH groups. This chemistry is actually how hair perms work. Yeah. You use a reducing agent to break the disulfide bonds in your hair keratin protein, reshape the hair, then use an oxidizing agent to form new disulfide bonds, locking in the new shape. Redox chemistry in hairstyling.
Wow. Okay, so proteins are sensitive to both pH and redox. What about just cleaning, getting rid of germs and grime?
Oh yeah, cleaning, sanitizing, disinfection. It's often chemical warfare using acid, base, and redox.
Acidic cleaners, like vinegar or citric acid.
They work partly by lowering the pH. For microbes, that can mess up their enzymes and protein function, inhibiting growth, often bacteriostatic. For mineral deposits like limescale, which is alkaline calcium carbonate, the acid neutralizes and dissolves it.
Makes sense. Alkaline cleaners, like oven cleaner with lye, NaO, or bleach.
Alkalis are great at attacking organic stuff, especially fats and proteins. They hydrolyze the ester bonds in fats, saponification, making soap essentially, and the peptide bonds in proteins, basically dissolving grease and food residues. Bleach, sodium hypochlorite, NaClO, is alkaline, but its real power comes from something else.
It's an oxidizing agent, too.
Yes, that's the key for sanitizing. Many powerful disinfectants are strong oxidizing agents. Hydrogen peroxide, ozone, and chlorine bleach are prime examples.
How do they kill microbes by oxidizing them?
They basically attack and damage essential molecules in the microbial cells, proteins, DNA, lipids in the cell membrane by stealing their electrons. Hydrogen peroxide generates reactive oxygen species. Ozone is incredibly reactive and tears apart cell membranes. Bleach, NaClO, in water forms hypochlorous acid, HClO.
HClO.
Yeah, HClO is a weak acid, but it's a very strong oxidizing agent. And because it's small and uncharged, it can easily slip through bacterial cell membranes and wreak havoc inside, oxidizing crucial components. Interestingly, HClO is actually more effective at lower pH, but the bleach solution itself is alkaline for stability.
So cleaning uses pH to dissolve stuff, and redox to destroy germs and stains.
That's a good summary, leveraging those fundamental reactions.
And the applications list just goes on, doesn't it? We mentioned batteries.
Yeah, electrochemical cells designed to produce electricity from spontaneous redox reactions. Primary batteries run once, secondary ones, rechargeable, can have the redox reaction reversed.
Titration in the lab.
Classic analytical technique. Use a carefully measured volume of a known solution, acid or base or oxidant or reductant, to react completely with an unknown solution to find its concentration. Relies on stoichiometry of neutralization or redox.
And industry must use this stuff constantly.
Absolutely. Making ammonia via Haber-Bosch involves redox. Making nitric acid via the Ostwald process, electroplating metals onto surfaces, is redox. Wastewater treatment uses pH adjustments and often oxidation or reduction steps to remove pollutants. It's truly everywhere.
It really is. Okay, so wrapping this up, We've taken quite the deep dive here, using the source material as our map through acids, bases, and redox.
Yeah, we've gone from the basic definitions, Arrhenius, Brensted, Lowry, Lewis, and the scales we use, like pH, pKa, E degrees, all the way to seeing how these transfers, protons or electrons, drive just countless processes.
It's clear these aren't just abstract ideas in a textbook. They explain why vinegar cleans limescale, why iron rusts, how our blood stays stable, how batteries work. It gives you a really powerful chemical lens to view the world.
Definitely. Understanding how structure dictates properties, how conjugates relate, how electron flow creates energy or causes decay. It connects so much chemistry and biology together.
So next time you squeeze a lemon on your fish or see a rusty nail or even just breathe, remember you're witnessing solution chemistry, acid base, and redox in action.
It's all around us, and here's maybe something to chew on after this.
Yeah.
We've seen how interconnected all this is, right? pH affects redox, ions affect reactions, biological systems depend on delicate balances. So what happens when we throw a major wrench in the works?
Like large-scale pollution.
Yeah. Say something dramatically changes the pH of a lake or introduces new chemicals that act as strong oxidants or reductants into an ecosystem. How might that initial chemical disturbance cascade? How could it affect everything from, say, the solubility and toxicity of heavy metals already present to the function of proteins in aquatic organisms, maybe even the corrosion rates of underwater structures? Makes you think about how fragile these chemical balances can be on a larger scale.
That's a great point. Lots to think about there. Keep exploring. Keep noticing the chemistry happening all around you.